Hi. If you've not already printed out a copy of the lecture notes and want to do that to take notes, they're posted on Learning Studio, so feel free to pause the video and do that. We're still going to be investigating the convergence or divergence of sequences, and the method that we're using in this particular lesson deals with subsequences. Subsequences have many other uses as well. So here is the official definition of a subsequence. The idea is really very simple, so let's go straight to examples. Here I have the sequence minus a half plus a fourth minus an eighth plus a 16th and so on. The rule that's giving this is minus a half to the n. So powers of a half, but then alternating between negative and positive. So for a subsequence, you talk about a subset, an ordered subset of the indices. So the indices go the first term, the second term, the third term, the fourth term, and so on. Let me just write something down. I choose n1 equals 1, n2 equals 3, n3 equals 5, etc. So nk, in fact, is 2k minus 1. I'm just picking off the odd indices, and this goes on forever. So then, from the original sequence, we can talk about the subsequence, a sub n sub k. And what values are in that sequence? Well, the first term of the original sequence, so minus a half, and the third term of the original sequence, so minus an eighth, and the fifth term of the original sequence, so minus 1/32, and so on. So every term of this subsequence was a member of the original sequence, and they appear in the same order. So up here, minus 1/2 occurred before minus 1/8, occurred before minus 1/32, and likewise in the subsequence. Other than that, I'm just going through the original sequence and making an arbitrary choice about which elements to pull out. Here's another example. A sequence alternates between 0 and 1. So let's form several subsequences here. I can choose the rule that n sub k is going to be 2k minus 1, which is just a list of odd integers. And so, in fact, this defines the subsequence b sub n sub k. The notation's kind of cumbersome. And it picks off the first and the third and the fifth, and so 0, and then the next 0, and then the next 0, and the next 0, and so on. Or completely independently, I could have done, say, j sub k, another sequence of indices to be 2 times k. And then a subsequence of b sub n is b sub j sub k is, well, these are picking off the even terms, even indices. So the second, the fourth, the sixth, and so on. That's just 1, 1, 1, 1, and so on. And completely independently, I could pick L sub k to be just, say, k, and then B sub L sub k is, well, this picks off everyone. So this goes 0, 1, 0, 1, etc., which of course is the original sequence. So every sequence has itself as one of its subsequences, and then probably many other sequences as well. In terms of convergence and divergence, notice that the original sequence b sub n diverges. It just bounces back and forth between 0 and 1. But b sub n sub k, this subsequence, clearly converges to 0, and b sub j sub k, this subsequence, clearly converges to 1. So there's some relationships going on here about when sequences converge and when subsequences converge and when they don't. And here are a couple of rules. The first part of this theorem says that a sequence converges to a particular number if and only if each of its subsequences converge to that number. So as a convergence test, I could come back here, if I didn't already know that b sub n diverged, I could say that, okay, b sub n sub k converges to 0, but b sub j sub k converges to 1. Those two numbers are different. So I have two subsequences converging to different numbers, and therefore the original sequence cannot converge. And this should make sense if you think about it a little bit. If the original sequence is converging to a particular number, and I pick a subsequence, no matter which of the dots I choose, if all of the red dots are converging to 4, say, then any choice of black dots that I make along the way also has to converge to 4. The other part, kind of unrelated part to this theorem, is that every sequence has a monotone subsequence. So let's actually prove that. And it's a little tricky, at least the notation is. If I start with a sequence an, let's consider the set of integers. So eta is the set of integers. It's every integer n, and here is the definition. It's a simpler concept in English. I'm going to put an index in if that term is smaller than any I'll see from here on out. Let's look at an example. If this is the original sequence, or this is the sequence, then let's just build eta from scratch. I look at the first term and say, is that at least as small, or no greater than, any term that I'm ever going to see in this sequence again? And this is the -1/2, +1/4, -1/8, +1/16. Yeah, -1/2 is the smallest element that will ever be in this sequence. It's the first term, and so 1 goes in this set. How about 2? Is 1/4 the smallest thing that I'll ever see from here forward? No, the very next term is -1/8, which is less than that. So 2 is not in there. Third term is -1/8. Is that as small as anything that occurs after it? And the answer is yes. So 3 is in here. 4, the 1/16th, is not the smallest thing from there on out, so it's not in there. The fifth term is, and so on. So here's an example where members of this index set eta are the odd number terms. How about a sequence that goes 3, 1, 2, 2.1, and then the pattern starts after the 2.1 is 2.01, and then 2.001, 2.0001, and so on. So here we go. Is the first index in there dealing with the 3? Is that as small as anything I'll ever see again? No. So 1 is not in there. Second term, is 1 as small as anything I'll ever see again? Yes. So 2 is in there. Third term is 2. That's as small as anything I'll ever see in there. So 3 is in there. Fourth term, 2.1. That's not as, there are things smaller than 2.1 after it. So 4 is not in there, the fourth term. And likewise, the 2.01 has smaller things after following it, and 2.001 does as well. And so, in fact, here eta is a finite set. Only the second and third terms are the smallest from there on out. And how about a sequence that's 1, 1/2, 1/4, 1/3, 1, 1/2, 1/3, 1/4, 1/5, and so on. First term is not the smallest. Second term is not the smallest. Third term is not the smallest. Fourth term is not the smallest from there on out. Everybody is followed by things smaller than itself. And so here's a case where this index set is actually empty. So depending on the original sequence, we can get an infinite set for eta, a finite set, or even an empty set. And now let's prove number 2, that every sequence has a monotone subsequence. So proof of 2. Let's do this by cases. Case 1, when eta for this sequence is infinite, as it was for sequence an. So let eta equal n1, n2, n3, ... forever. Eta is already defined. I'm just saying let's call the first thing in eta n1, then n2, then n3. And we know that n1 is strictly less than n2, which is strictly less than n3, which is strictly less than, and so on. Well, what then can we say about a sub n sub k? So that's an1 followed by an2 followed by an3. But the way eta was constructed, everybody that's in eta is as small as anything you'll ever see again. And so a sub n sub 2 can't be any smaller than a sub n sub 1. And an3 can't be any smaller than an2. And so this guy, in fact, if you see it, is an increasing sequence, which is one type of monotone sequence. Case 2. Case 1, eta is infinite. Case 2, eta is finite. Well, actually this case is going to be quite different. I'm going to construct a decreasing sequence in a different way than in case 1. So since eta is finite, it's bounded, and so there exists an n1 which is greater than the maximum of set eta. So it's greater than the maximum. N1 is greater than the maximum of eta. So N1 certainly is not in eta. And the way you be in eta is if you're as small as anything that will come after you. If you're not in eta, then there must be someone smaller after you coming along. So this is N1. So there exists an N2 greater than N1, so that a sub N1 is greater than a sub N2. So what I'm saying is N1 was not the index of a term that was the smallest from here on out, so give me a smaller one. Give me a N2 that's less than a N1, where N2 is farther out in the sequence than N1. Okay, but N1 was already bigger than the max of eta, and so N2, still bigger than that, is not in eta either. So, but then N2 is not in eta, and so I can do it again. So there exists an N3 there exists an N3 greater than N2, so that a N2 is greater than a N3, or a N3 is less than a N2. I found somebody smaller than a N2 because N2 wasn't in eta either. And here's a process, then I can find an AN4 here on out by the same pattern. So then A_k is a decreasing subsequence. All right, so the two cases were different, but they both led to a conclusion that there is a monotone sequence. And the reason we wanted that theorem is this one, the Bolzano-Weierstrass theorem for sequences. We've already seen the Bolzano-Weierstrass theorem for sets. It said that every bounded infinite set had a limit point, and so an accumulation point. And for sequences, the analog is every bounded sequence has a convergent subsequence. Well, let's prove this as well. It's easy if we have the previous theorem in mind. So by part 2 of the above theorem, AN has a monotone subsequence. ANK. Here's a key word, bounded. So I already know that this subsequence is monotone. If the subsequence comes out of a bounded sequence, it has to be bounded itself. Yeah, the original sequence is bounded, so any subsequence also has to be bounded. Now I have a bounded monotone sequence, and we know about those. So ANK converges by the monotone convergence criterion. Okay, so before we go on to another topic, just think a little bit about what that says. Certainly not every sequence converges, but if you're a bounded sequence, then at least you have somebody inside you that converges. So examples up here, for example, the 0101 didn't converge, but it is a bounded sequence, and so the Bolzano-Weierstrass theorem assures us that at least one of these guys exists. In fact, in this case, there are a couple of subsequences that I can take where the subsequence converges. And so if you're doing a proof that uses a convergent sequence, sometimes your sequence that you want to use isn't convergent, but you can still get by with extracting a convergent subsequence and then working with that one here on out. And in later analysis, you'd encounter situations where that's useful. So let's leave that. Let's go on to another topic. First, some notation. Let's define some sets coming from a sequence. So I have an original sequence A, N, A1, A2, A3, and so on. And I'll define psi sub n to be the AKs from n on out, so to speak. So easier to see by explicit example. Psi 1 is the entire set of terms starting with the first. Psi 2, everything starting with the second. Psi 3, everything started with the third. These are actually sets. I don't mean for these to be sequences anymore. If the elements are all distinct, then no harm done in thinking about it, but sequences have an ordering. Sets are just lists of numbers. We use this psi n idea to define the so-called limit superior and limit inferior. Very tricky concept, so let's walk through this slowly. I have a sequence in mind, and you do this for bounded sequences typically. So I have a bounded sequence in mind. I define its limit superior and write it this way, and often read it lim sup of an. It's the limit of the supremum of these psi n sets. So if I were actually constructing this, I'd work from the inside out. First, I'd construct psi 1, and then psi 2, and then psi 3, and psi 4, and so on. Then I'd take the supremum of each of them. So now I have sup of psi 1, sup of psi 2, sup of psi 3, etc. That generates a list of numbers, and then I'm saying I'm going to take the limit as n goes to infinity of that list of numbers. So we'll work some examples in a moment, but first let's assure ourselves that this is a definition that makes sense at all, because it involves taking a limit, and not all limits exist. Let's note, first of all, that there is a containment to this. Everything that's in psi 2 was also in psi 1, although not the other way around. Everything in psi 3 was also in psi 2, which was also in psi 1. So psi 1, the set, contains set psi 2, contains set psi 3, contains forever. And so what can we say about the sup of psi 1 as compared to the sup of psi 2 as compared to the sup of psi 3? Well, the bigger the set, the bigger the supremum, because you have more numbers over which to pick the largest, loosely speaking. And so these guys go this way. I think Chris actually proved a theorem for his lesson that was basically this problem. So now let's define an to be the sup of psi n. And then what can we say about the sequences of the ANs? Well, first of all, the original sequence, little a sub n, was bounded, so all of the psi's are bounded sets, and so the suprema, each of these supremums is a finite number and bounded as a list, and so a sub n is well defined. The psi sub n, the set of psi sub n's is bounded. So this is a bounded, and it's also decreasing. A1 is greater than A2 is greater than A3. But a bounded decreasing sequence is convergent. And so what we're saying is if we start with a bounded sequence, then even though the limit of that sequence may not exist, the sequence may not converge, the limit superior will exist and the limit inferior will exist. So that's a huge advantage of dealing with these concepts. For sequences that are bounded, these guys always exist, and I know they do, and I could work with them without even knowing ahead of time what the original sequence is doing. Now let's do some examples of finding these things. So here's a sequence Cn. It's the 0101 alternator again, and I'm interested in talking about what's the lim sup of Cn. Okay, back to the definition. In concept, I have to think about each of these A1, A2, A3, and so on. So starting from position 1 here, what's the biggest thing in this sequence that by the way, since the sequence was little c sub n, let me define capital C sub n, capital C sub 1, capital C sub 2, and so on, in the same notation as up above. Okay, from position 1, what's the biggest thing from the first element on out? Well, there are ones places in the list. How about if I start at the second element and go from there on out? What's the biggest thing I see? 1. What about the third element from there on out? What's the biggest thing I see as I go forward? 1. And of course I can keep this up all day long, and so the limit superior is now the limit of this sequence of numbers, and 1, 1, 1, 1, 1 has limit 1. How about the lim inf of C sub n? So what's the smallest thing I see starting at the first position and going forward? 0. How about if I start at position 2 going forward, what's the smallest thing I see? 0. Position 3, 0. Position 4 and forward, 0. And then what's the limit of the sequence 0, 0, 0, 0, 0? It's 0. So original sequence Cn has lim sup 1 and lim inf 0. Another example. How about the 3, 1, 2, 2.1, 2.01, and so on. Lim sup, lim inf, okay. What about B1? What is the starting with the first, what's the largest thing I see going forward? 3. Starting at the second, what's the largest thing I see going forward? 2.1. Starting with the third, what's the largest thing I see going forward? 2.1. Starting at the fourth, what's the largest thing I see going forward? 2.1. Starting with the fifth, what's the largest thing I see? 2.01. Now I'm past the 2.1. And likewise, what's the largest thing I see starting at the sixth and going forward? 2.001, etc. So these numbers are decreasing and therefore n-bounded. They have a limit. That limit is 2. About for the lim infs, starting at the first, what's the smallest thing I see looking downstream? 1. Starting at the second, what's the smallest thing I see? 1. Starting at the third, what's the smallest thing I see? 2. Starting at the fourth, what's the smallest thing I see? Okay. So notice that I don't have a smallest, when I'm here at the 2 and looking for, or the 2.1 rather, and looking forward, notice that I don't have a smallest element anymore. I can still talk about the infimum of this sequence though. The infimum of 2.1, 2.01, 2.001, and so on going forward is 2. And likewise, when I'm here at the here at the 2.01, here and looking forward, what's the infimum of the list of numbers going forward? 2. And likewise, when I'm here, and so on, every time past the first few, when I'm looking forward, the infimum of the remaining list is 2. And then I have what's the limit of a few numbers, and then 2, 2, 2, 2, 2, 2. The limit of that is 2. So the lim sup and the lim inf of this sequence are both the number 2. Finally, here's an example, the minus 1/2 plus 1/4 minus 1/8 lim sup of an. and lim imp of an. Okay. What about a1? When I'm here at the first element and going forward, what's the largest thing I see? 1/4. When I'm at the second and looking forward, the largest thing I see is 1/4. When I'm at the third, the largest thing I see looking forward is 1/16. When I'm at the fourth, also 1/16. When I'm at the fifth, the largest thing I see looking forward, and I'm right here, is a 1/32, and so on. So this is a decreasing sequence, and its limit is 0. And how about infimum? Now I play the game with the smallest guys. So I get the numbers -1/2, -1/8, minus a, let's see, did I do that right? +1/16. So this actually would be a +1/64. And over here I'd be getting numbers like -1/2, -1/8, -1/32, and so on. Those also have limit 0. So the lim sup and the lim imp of this sequence are also 0. Are both 0. Kind of tricky. That will take some practice. So back to our usage of this, the reason we want to talk about lim sup and lim imp for our purposes right now are what it has to say about convergence of sequences. So number 4 here, in some sense, is our goal. Excuse me. Before we get there, let's point out a helpful kind of diagram from the text that may help understand what lim sup and lim imp are a little bit. For purposes of writing this theorem, shorthand notation for lim imp of the sequence is little m, and for the lim sup of the sequence is capital M. So in particular, let's talk about capital M. It's the largest value to which infinitely many terms get arbitrarily close to. Picture, here's the lim sup, and now I'm going to draw the elements of the sequence on this number line. The precise statement of the theorem says, first of all, let's form an epsilon neighborhood. And then the lim sup is the largest value which is close to infinitely many terms. So that's saying in this little epsilon neighborhood that I drew, I actually know that there are an infinite number of terms from the original sequence in here. And because m was the limit superior, it's the largest m that I could do this for, I know that though there might be a few guys out here, this is a finite set. The set of stuff bigger than m plus epsilon is finite, no matter which epsilon I pick. And then down here, we don't know. And actually we don't care, because the limit superior is talking about how big can this number m get. So you can kind of see that back here, perhaps. The lim sup of this sequence is 2. If I drew the elements, you see there's 1 at 3, and 1 at 1, and 1 at 2, and then 1 at 2.1, and 2.01, and 2.001, and so on. Lots of stuff stacking up here. So 2 is the largest place that I can start and draw any epsilon neighborhood and still capture an infinite number of points. If I go to like 2.05 or something and draw a tiny epsilon neighborhood, there are only a finite number of points would be in that neighborhood. So 2, the limit superior, is kind of the largest number that's close to lots of points, largest number that's close to an infinite number of points. And then anything above 2 is kind of isolated, flagging out here by itself. Okay, let's keep walking through this theorem and talk about each part as we go. So let's given a sequence A sub n that let me start over. Given a sequence A sub n, we know that there may be subsequences in it that converge whether the original sequence did or not. So the starting sequence here is bounded, and so in fact there will be convergent subsequences, maybe one, maybe lots of them. Suppose I just go through all of the convergent subsequences that I can find and find the limit of each one of those. Let's take all of those limits that we found and throw them together into a set S. Then the biggest element in that set, the biggest limit point, or the supremum of the limit point, if there are an infinite number, is the limit superior. So another way of thinking about the limit superior is it's the superiors of the supremum of the limits. If I take all of possible convergent subsequences and what they converge to, the biggest thing that anybody converges to is the limit superior. You can kind of see that in this picture. If I tried to talk about something up here, no subsequence is going to converge to this green guy, but a subsequence will converge to capital M. So the set is infinite, so there's lots of stuff around in here that's bouncing around close to M. And that's part 3, that in fact there is a subsequence that does converge to the limit superior. And 4, for our terms, is probably the most useful of these. A sequence, bounded sequence, converges if and only if its limit infimum, or inferior, equals its limit superior. And in that case, the limit of the sequence is that common value of the lim inf and the lim sup. This kind of sounds like the squeeze theorem, perhaps. The lim inf is kind of the smallest the limit could be. The lim sup is the largest the limit could be. If those two numbers are the same, then the limit must exist and be that very number, in fact. Okay, let's prove 4. It's an if and only if. So there are 2 directions to prove. I'll go this way first. So I have a convergent sequence. Let's give its limit a name. Let A be the limit of sequence A sub n. And now I want to show that the limit inferior equals the limit superior. So the way you can show that little m equals big M is to show that little m is less than or equal to big M, and that it's also greater than or equal to big M. So to do that, we'll use the epsilon property. We'll show that the lim inf can't be much bigger or smaller than A, and also for the lim sup. Okay, fix epsilon greater than 0, and let's choose a natural number This is definition of convergence of a sequence. Choose a natural number so that an minus a is less than epsilon whenever you're farther out in the sequence than this number n. This is a capital N. Okay, but kind of unraveling with the things like the triangle inequality here. If everything out far in the sequence is close to a, then no an can be any bigger than a plus epsilon. All right. But if all of the tail of the sequence, these ANs are way out in the sequence, if all of these ANs are less than a plus epsilon, so is the supremum of that set. Possibly equal to, but certainly no bigger than a plus epsilon. If we just kind of recap what we've said, thus for m, phone is ringing, I'll ignore that. Thus for m greater than capital N, a sub m is less than or equal to a plus epsilon. And thus the limit superior of the a sub n's is less than or equal to a plus epsilon. All of the guys far out in the sequence are less than or equal to a plus epsilon, and so if I take the supremum of all of the guys far out, that's also less than a plus epsilon. So I've shown that the limit superior is less than a plus epsilon, but epsilon was arbitrary, so by the epsilon property, limit superior of an is less than or equal to a. And we could have played an entirely analogous game with the lim inf. So let's just say similarly, the lim inf of the a sub n's is greater than or equal to a. And therefore what we have shown is that the limit superior of the an is less than or equal to a, which is less than or equal to the limit inferior of the an. But now think back to the definition of lim sup and lim inf. They were very closely related, but the lim sup talked about taking the supremum of a set, and the lim inf talked about taking the infimum of that same set. So by definition, the inequality the other way around is true. By definition, lim inf of an is less than or equal to lim sup of an, and now this inequality and this inequality together show equality. Therefore, lim inf of an does equal lim sup of an. All right. And let's prove the other direction. So I want to prove that if the lim sup equals the lim inf, that the original sequence converges. So here we're supposing or given that lim inf of an equals lim sup of an. Let's call that number a, and we want to show that the whole sequence converges to a. This part's a little different. We're still going to fix an epsilon positive. since A is the limit over n of the capital ANs, where AN is the set that we were talking about, the supremum of the sets as you start at a point and go there on out, and then advance one and go there on out. Since A is the limit of these sets, there exists, say, an N1 so that A and the limit of the ANs is not far apart. And is that what I want to do? I'm sorry, let me back up here. I'm kind of in alphabet soup. Let's come back and more explicitly talk about A. This is the limit of the supremum of the AKs for k greater than or equal to n. And therefore, now we're going, there exists an N1 so that A minus the supremum of the AKs for k greater than or equal to n is less than epsilon whenever n is bigger than n1. Okay, what that says is that the supremum of the AKs for k greater than or equal to n is less than A plus epsilon. Alright, the difference between these two, the A and the supremum, is less than epsilon, so the supremum less than A plus epsilon for n large. And if the supremum of all of these guys weigh out and the sequence is less than A sub epsilon, each of the terms are. So therefore AN is less than A plus epsilon for n greater than n1. When I go out far in the sequence, the terms have to be less than A plus epsilon, and then similarly there has to be an n2 so that AN is greater than A minus epsilon when you're out past n2. And so let's let n be the maximum of n1 and n2, which lets us conclude for n greater than capital N, the difference between AN and this number A is less than epsilon. But that's exactly what it takes to show that AN converges to A. It's the difference is less than epsilon for any positive epsilon. All right, we'll stop there. Thank you.